We don't want it to be too
Okay,
much.
can this be heard? Laura, can you hear me?
Yes.
Can you unmute yourself?
Yes.
Wow, it's really
I know, just zoom up. Okay.
All right.
Turn that one down. Put it up.
very sensitive.
It's very sensitive. Yeah.
Just a start.
Zoom this.
This is the most annoying reference. Okay,
Yeah.
that's good.
Yeah.
All right, okay.
We have to do one more thing to make sure your mics are unmuted. Zoom settings, and we want to do 1, and then we want to do 2 to unmute the microphones. So now that and the room microphones are unmuted. Your camera shot is good. And I want to turn this up a little bit because it was a little bit low.
Okay, 1, 2, 3.
Okay, we need to.
The mouse, use the mouse.
Oh, we need to mute your left, and then we can turn this off.
Okay. All right, perfect. Got it. Before
Can
we
you hear
begin,
me?
so why am I not sharing my screen? Right, but why is it sharing only that portion, showing the entire screen as opposed to just the green portion?
It's selected as just sharing that window.
Yeah, but then it's showing the entire screen.
Yeah, so what's gonna happen is because we have this plugged in with the HDMI, as soon as you go full screen on this, it won't show your whole. That's because it's just, when you plug this in with the HDMI,
Okay.
it's gonna just duplicate like this.
All righty. Okay.
So you just have to go full screen.
Yeah, so let me stop sharing first. And so Laura, can you say something?
Yes. Can you hear me?
Yes. Okay. So guys, all of us are headed out. So everyone, we're going to be stepping out for a couple of minutes. We're going to be stepping out for a couple of minutes. And Laura Potmaya from the Eberly Center is here. She's going to tell us about what we will be doing in this class. And you will, I assume, implicitly or explicitly be granting permission for whatever we're going to be doing, which is pretty innocuous. And then I'll be back. And how long will this take, Laura?
About 4 or 5 minutes. And would you be able to pause the recording when you leave?
I have not begun recording.
Oh.
I think I have not begun recording. Let me just check. So how does one pause the recording? This one.
You can pause it, yes.
Okay, this one pause. Position invariant. Oh shit. So has the recording begun? Okay. So we're going to be talking about shift or position invariant detection of patterns. So far, we've been looking at how can you classify an input. Just when you're presented the input, you're not worried about the structure of the input itself. So here are, is this working? Nothing works. What? All right, I'm anchored. Or maybe even that doesn't work. So the story so far is that MLPs are universal function approximators. They can be trained through variations of gradient descent. And the model so far has been this kind, where you have an input and the entire input is passed through your network, and it makes a prediction. So the input could be images, it could be vector data. We've seen examples of both. But now here is the problem. I've given you an audio recording, which is being represented as a spectrographic matrix. So you have a sequence of vectors. Each vector represents a spectrum of one small slice of the audio. And my question to you is, does this recording contain the word welcome? So we want to build a neural network that answers this question. We know how to do this, easy enough, right? I can just, this entire thing is my input. I can just construct a neural network that takes the entire input. It makes a classification. This is what we've done so far in our homeworks. No big deal, right? Here's the question. I have 2 different recordings. One of them is the one on top where the word welcome is to the left, and the other one where the word welcome is to the right. Will a network that has been trained or that is good at detecting the word welcome on the left also be able to detect that the word welcome has occurred when the position has shifted? Would it be able to do so? Why not? Can anybody tell me? Yes. So you're right, but there's mathematically a very simple reason for this, right? So if I think of the entire thing as a vector, then when the word welcome occurs, you're going to have some, say, let's say binary numbers of this kind, and the pattern is going to occur in some portion of the vector, right? If I shift the word, now the word welcome occurs here. So your vector is going to look something like this. I'm just assuming binary vectors, but you get the idea, right? Are these the same vector? One is the x-axis, the other is the y-axis. They're completely unrelated, right? So clearly something that detects the word welcome in the first position will not do so in the second. So I want a simple network that will fire regardless of the location of the word welcome. So how would you do this? So how would you do that? Anybody? Yes.
Try to get rid of the exterior zeros and just look for.
But so the point is there's a continuous speech. There's no zeros. So there are no zeros, right?
Like in our homework one, we just looked at we kept on feeding kind of a constant section into our network.
We can scan. All of you are right? So here's the same problem. Again, for images. I'm looking for flowers, right? Will a network that can detect a flower in the top left image be able to detect flowers in the bottom right one? Yes or no? Right? And for the same reason that we had here. So we need a network that will fire regardless of the precise location of the object. So what we are really interested in is shift or position invariance. In many problems, the location of the pattern is not important. It's only the presence of the pattern that is important. And conventional MLPs, as we saw, are very sensitive to the precise location of the pattern. Moving it by even one component is going to completely change the space that the pattern lives in, and it will not fire. What we want is a very simple, we don't want a complicated thing. Now, there's a naive solution to this. I could just train the network with pictures of flowers with flowers everywhere. But then in order to train such a network and for it to be able to memorize every position of the flower, the network would have to be enormous. And the amount of training data that you would need would also have to be enormous because it would have to consider every possible position of the pattern. So clearly that is not a solution, right? We want something simple that will fire regardless of where the pattern occurs. So here's how we could do it. We can scan. I have my little welcome detector. And it looks at the first, this is basically what Michael was saying. I can have a welcome detector. It looks at the first word of my recording, first position, and then I can sort of keep scanning for the word welcome through the network, right? So at this position, I have sort of analyzed every single position in my recording, and I have an answer. Does this position have the word welcome or not? But my question was not, where is the word welcome? My question was, does this recording have the word welcome? So how can I combine all of these to decide whether the recording has the word welcome? I can OR, right? And an OR is basically, in this case, it's just a max because these are soft decisions. So if the word welcome happens, then the output of the network is going to be high at least one position. So if I pick the maximum and I find that the maximum is a 0.95, then somewhere in the recording, the word welcome has happened. And so I can decide that it does indeed contain the word welcome. It doesn't need to be a max. I could be, for example, if you want strong evidence, if you keep detecting the word, if you say no welcome, no welcome, no welcome, welcome, no welcome, and if a shift of one position completely changes the decision the network is making, this is probably noise, right? Because sounds, they kind of smear. So, or images, you can't be very precise about the location. So maybe you want to do something like a soft max, which combines evidence from several neighboring positions. or even pass the whole thing through an MLP. But the point is, yes.
How is this affected by the size? You have two different flowers, for example, different sizes.
Assume for now that they're all the same size, right? That you have a flower detector which can capture a range of sizes. Okay. So long as you're within some range. It's like the other classification problems that you've been looking at. There's some variation that you can always learn to detect, right? So this is what scanning with an MLP looks like. You're going from left to right. At each position, you're sectioning out a segment of the input. You're putting it through an MLP, and you're getting a decision. Eventually, you have a collection of decisions, one per position. You put the whole lot through your softmax, and you decide if the word welcome has occurred or not. And so this now here's the thing. Yes. A group of 3, correct? So here's the thing. At each position, the input has been analyzed by a network. But then all of these outputs have gone into another unit, which can also be considered just an extension of the original network, right? This entire thing is not scanning with a network. It is one giant network, right? How is this different from conventional networks? Can anyone tell me? The answer is staring you. It's on the slide. I've told you before. When I ask you a question, the answer is usually on the slide. Yes. All the subnets are identical. Thanks for reading the slide. So now this is a shift invariant network, but all the subnets are identical, right? So this entire thing, that softmax is just the final layer of the overall network. This entire operation, I can say, is one giant MLP. Everyone with me so far? Right?
Does that mean I could just like have one word or that network have it multiple times?
Yes, you could, but then yes. In principle, yes, right? But that's the easy solution. But we want to do something a little more complex than that. We'll get to this, right? So same thing with the case of the flowers. In the case of the flowers, I can build a network that can detect flowers. I can scan the input position by position, right? And at each position, the network is deciding whether there's a flower at that position or not. I get a collection of outputs, one per position. I put the whole thing to a max. If the highest value is substantial, then I know that somewhere in the recording, the word flower has happened, right? So now, in terms of code, what would you be doing? Same thing. You're scanning the input left to right, top to bottom. At each position, you're sectioning out a little portion of the image. You're passing it through the MLP. And then you're taking the collection of outputs and putting it through a softmax. So once again, this entire thing can be viewed as just one giant network, with the distinction that, what was your name? Pardon me? Alex. Okay, I'm going deaf. All right. But anyways, so just as Alex just enlightened us, all of those subnets are identical, right? And so this is, but here's the other thing. In the process of making the network in this manner, we have come up with a very simple network. I'm calling it simple because you're really focusing on the subnets, right? That is shift or position invariant. I can shift the position of the basic pattern, and it's still going to fire. And so this entire thing is just one giant MLP. The last softmax is the final output layer. I could have written it like so, giant MLP. Now, 2 poles. Binoculars to read everybody's names. This should be actually big bright colors. Need to write this out. We got it. All right. All right, 5 seconds, guys. Done. Here's my clock. All right. Here are the answers. We can determine if a picture has a flower by scanning it for a flower with an MLP. This is obviously true. Scanning it to determine if the picture has a flower is the same as analyzing the entire image with one large shared parameter MLP. So what do I mean by a shared parameter MLP? Can somebody tell me? That's good. To go back to this picture, what do I mean by a shared parameter MLP? The subnets are identical. So when I train the subnet, if I modify the parameter of one of those subnets, I must modify the parameters of all of them, right? All of the subnets have shared parameters. Everybody clear? Okay. So now, just a little bit, I'm going to modify the visualization just for the purpose of illustration, because we'll be using it again and again. In a regular MLP, every neuron in a layer is connected by a unique weight to every unit in the previous layer, right? Why is this here? These are supposed to be. So these are supposed to be skipped. Okay. I'm not even sure why they're visible. All right. So I'm going to just modify the visualization for intuition. What we wanted to do was, let's say I'm scanning for inputs, for patterns that are 2 inputs wide, then I'd be doing something like that and then combining all of their outputs for a final decision, right? But then observe the pictures that I've shown with horizontal bars are kind of, they're conveying the wrong impression. It seems to give you the idea that the yellow computation occurs after the red computation within any horizontal bar, because I've drawn it horizontally, right? You don't want to do that. I'm going to change the picture to this. So I'm going to draw this vertically. Every little bar is actually a set of 3 neurons, which is analyzing the block underneath and is occurring at the same time. And so now you can see every bar represents one block of time, right? In this particular, because here you're scanning along time. And the first rectangle has 3 neurons at the bottom. Those are the first hidden layer, which are analyzing the input. The second rectangle has 3 neurons, which are reading the 3 inputs from the previous layer. So there are a total of 9 weights. And then the third rectangle has 2 neurons, which are analyzing the outputs of the 3 neurons in the previous layer, a total of 6 weights. And all of their outputs are going to the final output. And instead of making the picture so complex, I'm just going to show it like so. So when I show you an arrow from one block to the other, that means every neuron in the lower block is connected to every neuron in the upper block. So is this visualization making sense to everyone? Yeah, right. So this is what a visualization would be for a scan with a stride of 1. What do I mean by a stride? Every time I analyze a position, then I have to move. How much do I move by? If I move by 1 position, I call it a stride of 1. If I move by 2 positions, it's a stride of 2, right? Okay, training the network. When I train the network, I have to make sure that if I update the parameters of any one of the subnets, I want to update the parameters of all of the subnets. Now, to answer Michael's question from earlier, why is this different? Why couldn't I have just begun slicing portions of the image out or the recording out and just train a welcome recording to a welcome detector? We're not going to do it. My training data is, yes. I wish I could. I mean, this thing is a technical disaster. I can try. It's supposed to go away on its own. Somewhere here. Where's that? I need my glasses. That's how bad it gets, right? It's high floating media. Okay, thank you. All right. Okay. So now here's what we want to do. When I'm training the model, I'm not going to give you recordings with the word welcome tagged out. I'm not going to give you pictures where I've marked off the flower. All I'm going to give you are pictures with flowers and pictures without flowers, right? And so That is what, because that is the task the network is performing, right? And that is the kind of data that I will have, and that is the data I'm going to be using to train this model. And in the process, somehow magically, just with this completely weakly labeled data, where you are not actually identifying the location of the pattern you're trying to detect, the model will learn to find these patterns. And so how would you train it? Oh, gosh. Are we back? Okay. All right. So now, so here's what we are going to do. We can just use conventional backpropagation to learn the parameters, provide many training examples of images with and without flowers. And the target output for flower images is 1. For non-flower images, it's going to be 0. But then I have to modify my backpropagation rules to account for the shared parameter. How do I modify that? Now this won't work. Okay. These are shared parameter networks. So all lower level subnets are identical, which means any update to one copy of a subnet must update all the other copies. And so now we have to deal with learning rules and shared parameter networks. What are these? Consider this example where, now if I go back to this model, right, there are edges in every subnet which correspond. They all have the same value. So consider this trivial example where, yes.
When we label the whole image as having a power, the subnet focusing on the part which doesn't have a power also gets labeled positive, right?
No. The network gets labeled positive. The final output, each of the subnets has got to figure out what it does, right? You're not assigning any labels underneath. That's a classic problem we spoke about in lecture 3, right? So, okay. Now let's say I have a network where I know that these two highlighted edges have the same weight. Now, both of those have the same weight, WS. And the two weights are Wij and WLM. Forget about the superscript for now, right? So what does this mean? How do we compute derivatives? If I want to update the weights, I would really want to update WS, not the individual weights. And in terms of derivatives, any small perturbation of WS is going to modify, this also answers your question, modifies both weights, right? And both of those modifications are going to perturb the output. So if I were to draw the dependency diagram, that's what it's going to look like. WS is going to be perturbing each one of the individual weights, and each one of those in turn is going to be modifying the output, influencing the output. So if you use the derivative rules that we saw, the chain rules that we saw in previous classes, here's what we have. The derivative of the divergence with respect to WS, which is the shared value for all of these edges, is going to be the sum over all of the paths of the derivative of the divergence with respect to WMN times the derivative of WMN with respect to WS, plus the derivative of the divergence with respect to WIK times the derivative of WIK with respect to WS. What is the derivative of WIK IJ with respect to WS? 1, because they're identical, right? We said Wij equals Wmn equals Ws. So the second derivative is 1. You just end up with the partial derivatives computed for the sum of the partial derivatives computed for the individual edges that share the parameter. And so this is how we're going to have to change our derivative rules. When you compute derivatives for gradient descent, the derivatives are going to be with respect to the shared common value. And the derivative with respect to the shared common value must be obtained as a sum of the derivatives computed for each of the weights that share that value. But then, of course, for any individual training instance, those partial derivatives within the sum will be different. The locations where you don't have flowers will have a different influence on the output than the locations where you do have flowers. And so the partial derivatives will differ depending on which particular weight you are considering. And so here's what the back propagation rule is going to look like. The gradient descent rule is going to look like. The gradient descent is going to be updating the shared parameter with using the derivative with respect to that shared value ws. Ws is going to be updated. And so the key thing is being able to compute the derivative of the loss with respect to ws. And that in turn is going to be computed by summing over the derivatives that you get for each of the parameters that share that common value. And those final guys are going to be computed using backprop. So is this clear to everybody? May I see a raise of hands? Right? Any questions? Okay. So story so far, I'm behind, so I'm kind of rushing through. We have 280 slides, I'm at 72. Okay. So position invariant pattern classification can be performed by scanning, 1D scanning for things like sounds, 2D scanning for images. This concept can be generalized to higher dimensional data. You can have 3-dimensional scans. Scanning is equivalent to composing a large network with repeating subnets. And so backpropagation rules must be modified to combine the gradients from parameters that share the same value. And this principle applies in general for networks with shared parameters. We're going to see this business of shared parameters again and again and again. So please remember that, right? So now let's take a closer look at this entire business of scanning. Let's say I'm scanning this input for the word welcome. That picture to the left, that's the vertical representation of the network to the right, just to reuse the old notation, right? So at each location, so the lowest layer is the first hidden layer. And at each location, every one of the neurons at the lowest layer is going to compute a value shown by the little blue dots. And now those values all are going to feed to the next layer, neurons. And those neurons are going to compute their own values shown by the 2 little green dots. Those values are going to go up to the next layer, and which will compute its own value shown by the little gray dot, right? So what happens when I scan the input? At each position, the entire network is going to compute all these values. First, the lowest layer is going to compute those four blue dots. The value is represented by the 4 blue dots. Then the next layer is going to use those to compute the green values. And then the next layer is going to use those to compute the gray value. And you're going to do this at every position, right? Like so. And then finally, all of the gray values are going to be passed to your softmax. This is how you would perform the scale. Everyone with me? Right, okay. Let me change the order. The first block now computes its values. But then instead of waiting for the rest of the network downstream to perform its computation, the first block hurries on and scans the entire input. And now the second block kicks in and reads the value from the first position and computes its values. Will the output of the network at this position have changed? No. Right? Just changing the order of operations does not change anything, right? And so now I can do the same thing here. This output does not change due to the reordered computation, but now I can have the second block scan. But what does the second block scanning? Is it scanning the input? It's scanning the output of the previous block, correct? And so it can do that. And then the final output over here is going to be the same as before. And now that can perform its scan, right? And then I can do my final softmax. All I have done is change the order in which the computation has been performed. Nothing but the final output should not change, right? So in terms of code, what does it look like? At each position, what we were doing earlier was pulling out a segment and putting that segment through the MLP and then doing a final softmax. So if I zoom in on this business of MLP, that MLP is actually putting that portion through several layers, starting from the first hidden layer all the way to the output layer. And each layer is operating on the outputs of the previous layer, first computing an affine value and then computing an activation from it. This is the standard MLP, right? Now, look at the blue. What's happening? All the computation is happening inside the blue shaded area. The loop indices are outside. if I change, so the first loop index is over time, the second loop index is over layers. If I change the order of these loop indices, will the final output change? Why will it not change? What does this have to do with back propagation? This is, okay, you there, one person sleeping in the middle. So can you tell me why this will not change? Why changing the loop index will not change the output? Yes. Can you tell me? Anybody want to answer? This has nothing to do with layers. Yes, tell me. So this has nothing to do with layers per se, right? This is programming. When I have nested loops, if all the computation is happening inside the innermost loop, changing the order of the indices outside will not change the output, correct? How many of you remember that? Raise your hands if you do, right? This has got to be sort of, and some of you are not raising your hands in the middle. So did you have a problem with that concept? You guys, that makes sense to you? Okay, so basically that's basically what happened. So in the vector notation, I just wrote it like so. We just changed the order of the loops. Same thing in 2D, right? So here's what happens. I have this network which is scanning the input, and the entire network is sort of analyzing the entire block and computing a single output. But then, so this is basically what we were doing. We were scanning the entire input of the network. But suppose just the first layer neurons scan the input. Now, when the first neuron scans the input, and I arrange the outputs in the same order as the input itself, it's actually going to create a map. But that neuron has performed its computation independently of every other neurons. And I can do the same with all of the first layer neurons. Now, if I want to find out if that red block actually has a flower, all I need to do is to pick up the corresponding location from the maps of the produced by the first layer neurons and pass that to the rest of the network. And will this be the correct answer? Right? Can I hear a combined yes? Yes. Okay, thank you. Right? So we need to be certain of this. Everything builds off of this. Now the second layer neurons can do the same thing. They can scan the input like so and form their own maps. And then to decide if there's a flower in the central block, I just have to pick the corresponding location from their maps and put it through the rest of the network. And of course, I can recurse. The third layer neurons can scan the outputs of the second layer neurons. Now, here's something key that happened. When the second layer neuron was scanning the output of the first layer neuron, remember, when the first layer neurons were scanning the input, they were just looking at a single image, correct? The second layer neurons are actually looking at all of the images produced by the earlier layer neurons simultaneously and doing the scan. The distinction visible here, right? Smart, so this is what we're calling our channels. And of course, this entire thing can be put through a softmax or whatever else. The output should not change. So in terms of code, here is what was happening. We had the scan over X and Y, but within the innermost loop, which represents a specific position on the input, you had this computation. You went through the layers, and with each layer computed an affine value of the affine function of the corresponding region from the previous layer, right? And then you applied an activation. All we did was change the order of these outer indices. And this, as we know, should not change the final output because the actual computation is happening inside the innermost loop, right? So in fact, there are multiple ways of reordering this. I could be having just scanning over X, then going through the layers and then scanning over Y. I can be going through the layers and then each layer could be scanning over X and Y, and all of them should give you the same answer, right? So this is the modified code. So here is the story so far. Position invariant pattern classification can be performed by scanning the input for a target pattern, which is equivalent to composing a large network with shared subnets. The operations and scanning the input with a full network can be equivalently reordered as scanning the input with individual neurons in the first layer to produce maps of the input, and then jointly scanning the map of outputs by using the subsequent layers. Right? Yeah. Bear with me, right? So is everybody with me so far? Okay, yes. Things are going to get, yes, thank you. I noticed. That's what I noticed, that you were raising your hands in a, to acknowledge. So we are going to make this thing a little more complicated, right? What does all of this buy us? To see before that, actually a couple of polls. Five seconds, guys. Okay, you're done. Scanning an input image with an MLP is mathematically equivalent to first scanning with the individual neurons in the first hidden layer, then scanning the output maps of the first layer neurons with the rest of the network, right? And the operation can be recursed. This is also true. So we saw both of these. Now, moving on, what does the network actually learn? What do each of these neurons learn? Now, ideally, the entire MLP, of course, is trying to detect a flower, but then we've seen in earlier classes that the kind of representations we want is we want the neural network to learn its representations in a built-up pattern, built-up manner. Here, the first layer neurons look at the entire window to extract window-level features. So the features that they're going to detect are the size of the entire window. And then the subsequent layers are looking at only one pixel in the output of the previous layer neurons, right? So the first layer neuron is responsible for evaluating the entire window of pixels. And that all of that is being compressed into one number. And the patterns you're looking for are the size of the target pattern itself. But then we can distribute the pattern matching over two layers and still achieve the same block analysis at the second layer. So here's what we can do. We can, let me see if I think I've got some slides missing. So remember how we did this when we were trying to build up patterns when we were using other kinds of problems. When I was asking you to decide if, for example, a number was a digit or not, you wouldn't be looking for digit recognizers. You'd be looking for parts of digits. The most optimal manner in which to do it was to have maybe the first layer, hidden layer, look for lines and curves, which could form digits. And then the second hidden layer sort of compose these patterns. So also when we are saying, if I want to detect a double pentagon decision boundary, you didn't have just one hidden layer. The first hidden layer found all the individual boundaries. The second hidden layer composed this individual pentagons. The third layer combined the pentagons. You want to distribute the patterns over many, many layers because that is far more efficient. And we know that it's going to be much more robust. It's going to need far fewer parameters, and it's going to give you much more accurate outputs. So we want to transfer the same philosophy to this problem. We are going to distribute this representation. Instead of having the first layer neurons analyze the entire window, we are going to distribute the representation over many layers. The first layer will now look at smaller blocks, the size of the little white window the rectangular square that I'm showing, and it's going to create the maps. But now I want the second layer neurons to get a larger block, right? So if the second layer neuron now looks at a little rectangle or square of outputs from the first layer neurons, then what is the effective size of the actual input that the second layer neurons are looking at? It's going to be something much larger, right? So if for example, here, if it were 3 cross 3 that I'm looking at from the output of the first layer neurons, then the region of the input that was analyzed to compute those 9 outputs is what the second layer neuron is now looking at, right? And so this, and what has happened over here is now that the first layer neuron is going to be evaluating smaller blocks of pixels. The first layer neurons may not be looking for entire flowers anymore. It may be looking for sepals and petals and little stamens, right? And then the second layer neuron is going to be combining these to decide if there's some signature of a flower. So the window has been distributed over 2 layers, and the higher layer implicitly learns the arrangement of the sub patterns in the first layer. So it might know, for example, that if I get high values in the top left, top row, in the center, and the bottom right, then I must fire because there's a pattern, right? It's finding patterns within the outputs of the first layer neurons. And so now the second layer neuron can actually scan. Now again, it's simultaneously scanning the outputs of all of the map, all of the first layer maps, right? So the second layer neuron can jointly scan all the first layer maps, and each output of the second layer neuron represents the output for one full-sized window, right? And having done that, now if I want to determine if there's a flower in the top left corner, so what was originally being looked at earlier, the entire window was being analyzed by just the first layer neurons. And if I wanted to find out if there was a flower in the top left position, I just picked up that one pixel, the top left position, from the first layer neuron outputs. Now I can't do that. I have distributed the scan over 2 layers. To determine if there's a flower there, I have to look at the top left position from the output of the second layer neurons. So that making sense to everybody? Right. So, okay, yes, question?
When we distribute the scan, does that cause any loss?
No, right? So there is gain, there's gain, and there's loss. We'll get to that, yes.
My question was because we are distributing different small statistical power amounts. I don't know how we are going to go back from yes or no in the 4 units to no with an zero.
We are still not trying to determine. Remember, our question was never where is the flower. Our question was, is there a flower, right?
Yeah.
So we don't need to so we are not constrained to isolating. We don't, at this point, the flowers are actually being detected by the second layer neurons, not by the first, right? So, but as a matter of fact, in fact, it is still the output of the final layer neuron that is detecting the flower over here. It's just distributed the pattern over many layers.
So, like in the spectrographic light, you can actually use similar things to know where is the well.
So we will get to that, right? I'll show you the same example. And now, so I can just distribute the scan in this manner, and then the output of the final layer is going to give me, can be passed through my softmax to tell me if there is a flower or not. Now, to answer your question, do the outputs of the final layer identify whole flowers? Yes or no? Every single pixel in the final map, what is it looking for? Can anyone tell me? It doesn't matter how the lower layer neurons distributed the pattern, right? By the time you got to the output layer, each dot is looking for at a full-sized window and is trying to detect a flower over there. Make sense? Right? So out there at the final output, I'm still getting an answer for is there a flower at every position of the input, which can be put through my softmax. Right? Okay. So this is still just scanning with a shared parameter network, as it turns out. It's just that within each subnet, now you have shared parameter sharing. How is that? So let's say I'm looking at the input with a smaller window, the size of those little squares. Then the second layer neuron, so there are 3 neurons in the first layer. In that black box, each of the neurons in the first layer are going to produce 9 outputs, correct? And so the second layer neuron is going to be reading all 27 of these outputs, okay? And so where is the extra sharing of parameters? Every one of those 9 black dots is using the same set of weights to analyze the input, because those 9 dots represent scanning with a smaller box. Every one of those 9 red dots have the same set of weights, because they represent scanning the input with a smaller box. So also every one of the 9 blue dots represent shared parameters, right? And so the actual network now looks like this. It is still a shared parameter network. It's that the parameter sharing is not just at the level of subnets. Even within the subnets that are analyzing the block, you have additional sharing of parameters. So I can recurse this logic, right? Now I can have the first layer, the first level neurons look at even smaller boxes. I can have the second level neurons look at little groups of boxes from the first level neurons. And they're going to be looking at a bigger region of the input. I can have the third level guys looking at little groups of neurons from the second layer output, and they're going to be looking at that effectively looks at a larger region of the maps in the first layer output, and that in turn looks at the full size block in the input. All I have done is to recurse this distribution of patterns from the beginning to the end, right? And the outputs at the final layer are still looking at flower-sized window. They have not been compromised in any manner. So everyone with me so far? Okay. So again, the final classification would just take all of those guys and pass it to a softmax. So this, again, regardless of how deep I make it, I am still scanning the input with a network and collecting their outputs. When I begin distributing the networks, the features over many layers, the little subnet that is scanning the input itself has parameter sharing within it. And the more I distribute pattern, the pattern across the layers, the greater the level of sharing within the subnet. And we will see some more pictures of it. So basically, how does this whole thing change our pseudocode? Here was the kind of code we had earlier. We were scanning the input. At each position, we were pulling out a segment and then putting it through an MLP, right? So when we were scanning this in 2D without distributing the parameters, we were scanning over XY, then going through the layers. We flipped that. We began going through the layers first, but within each layer, scan the entire input. But now, here is what happened. Originally, when we wrote this code, only the first layer of the network was looking at a block of values from the input. Subsequent layers were looking at single outputs from the previous layers, right? The code actually became simpler now. Now every layer is going to be simply looking at a block of inputs, a little window of inputs from the output of the previous layer. So I'm going through the layers. Each layer is scanning the output of the previous layers, and at each position, it's pulling out a little rectangle or square of values from the map of outputs produced by the previous layer and operating on those. Now, for the whole thing to work, the outputs must be arranged, of every layer must be arranged in the same order as the input. If you didn't have distribution, this was not required, right? I could have analyzed the windows in any odd order and collected them. But now, because I'm looking at these the arrangement becomes important. So the output of each layer must be arranged in the same manner as the input. Now, this business of scanning the output, scanning maps, looking for a pattern, is what is called a convolution. So scanning is where you have some kind of input, and you have a little, what we will call a filter, and then you're scanning it to look for patterns. This business of scanning is called a convolution, and this entire network is called a convolutional neural network. Yeah.
So this whole entire convolution is like inspired from shifted invariance.
That's it.
If I ask like the flower to always be like the full size of the image, will the convolution still be useful, or NLP is
So if you've worked on MNIST, you'll find that your MLP probably is just as good as convolutional network, because that's basically what happens in that case, right? So you still have benefits, and we'll see, right? So I'll skip the pseudocode. Now let's see the same thing from the perspective of a 1D convolution, because there are some concepts that will come out more clearly over here. So let's say I'm scanning this network, this input with the network shown there, and I've shown the vertical notation that I will be using to the right. So the first layer neurons, if I were just scanning without distribution, the first layer neurons are going to be scanning the entire window of input, and then you'll be computing the entire output, right? But then if I'm beginning to distribute it, here's what will happen. The first layer neurons are going to be looking at a smaller size of the window. So that little red neuron would be analyzing the entire input with a window, maybe the size that I've shown by the rectangle. In fact, every one of the neurons in the first layer would do that. But now, if I want the next layer to look at the bigger window that is shown, how would I do it? Yeah. Stride a window. I would actually be looking at something of this size from the output of the first layer, correct? And that is going to be looking at the bigger window, as you can see, right? And now this I can, and so I will be scanning the output of the first layer neurons using a block of this kind. But now suppose I want the next layer neurons to be looking at an even larger portion of the input. Then how would I do that? I can look at a window of the outputs of the previous layer, right? And scan with it, and I'm going to get the outputs. So you understand what is going on, right? If everybody got what's going on in both the 2D and 1D case, raise your hands, please. Right? Okay. And so the final perceptron just aggregates the evidence to decide if the input has a target pattern, in this case, a word. When I'm doing this with time series data, this is often called a time delay neural network. Now, what is the point of all of this? To get to that first of all. This will be short. It's only one question, 30 seconds. Are there any questions? Okay, 5 seconds. Oh. This was easy. The second and the third options were right. The first and the fourth were not, right? And I'm assuming you've read the options. I don't need to explain. Now, why are we distributing things in this manner? Distribution forces hierarchical representations with localized patterns in lower layers. Fewer computations, fewer parameters. Let's see how the whole thing works. So first, how does it force hierarchical representations? This is the example that I showed earlier, right? I was discussing earlier. When we wanted to do the double pentagon, we saw it was much more effective to spread the pattern over many layers. Distribution actually forces this kind of structure. So also when we were trying to classify digits, it makes more if I have inputs which are little LED patterns, and I have to detect if that pattern is a digit or not. All I really need to do, I don't need to be scanning. Lady, can you actually shut the phone? Julia? Thank you. Right. So keep your phones off, guys. So it makes much more sense for me to be looking for individual lines and such like, and then combining those. So distributed patterns recognition makes distributed pattern representation makes a lot of sense. But then how do we deal with fewer computations and far fewer number of parameters? Where does that happen? So let's see this. Let's say I have tried to analyze the input over here, and the input using a network which does not have distribution. And the network is looking for patterns which are 8 inputs wide. So if that is what I'm doing, I'm going to have this one bar which scans the input, right? Now, assume, so basically this is the non-distributed scan. I am not representing the individual dots within the bars of an 8 time stepwise pattern with a stride of 2 time steps. So you're looking at a block of 8 inputs, then taking a stride of 2, then looking at another block of 8 and moving on. If there are N1 neurons in the first layer, so here is the picture, right? I have my inputs. My inputs are d-dimensional. I'm looking at 8 of these at a time. So these are 8, 1, 2, 3, 4, 5, 6, 7, 8. And then I have N1 neurons in the first layer. How many parameters do I have here totally? Can anyone tell me? N times 8 times d, right? Don't forget the d, correct? So everyone with me so far, right? Now suppose I have n1 times. So this is going to be n1, 8, n1d. Suppose I have a second layer, which is n2 neurons. How many parameters do I have connecting the first layer to the second layer? N1, N2, right? And so on. So you see how this works. And so I have N2, N3. And this would be if I did not have distribution. But now, if I'm distributing the analysis, here's what happens. First, I'm going to be analyzing the input with one layer, which is maybe looking at inputs 2 blocks, 2 vectors wide. The second layer, yes. I'm not ignoring the bias for now. Okay, the bias is just an additive term. This is, but you're right. So suppose I were distributing it. The first block may be looking at inputs 2 vectors y, blocks of 2 vectors. And then if I want the second layer to look at an input of 8 wide, it must be looking at 4 of these blocks, right? How many patterns do I have over here? So, okay. Now, if I want to have the same number of effective neurons, right, then how many neurons must I have in each block over here in the first layer? Each of them is going to have over here 2D and 1. So in this case, let's go back here. How many parameters would I have over here? Can anyone tell me? How many parameters would I have? The first each yellow block, all 4 yellow blocks are identical, correct? So they're only going to be looking at 2D and 1 parameters from the first block, right? But to compensate for it, the second block is going to be looking at 4 times N1, N2. And so the number of patterns is going to be, in general, 2D N1 plus 4 times N1, N2 plus N2, N3. Now, if I want to compare this, the total number of parameters, these things that are highlighted in green are the number of unique parameters, right? If I have the same number of neurons in the network, in the distributed versus the non-distributed network, each yellow block in this case is going to have 1/4 the number of neurons that you originally had, right? Because if this guy had 8 neurons in the first layer, and if I want the lowermost network layer to be the layer of the network to have 8 neurons, there are 4 identical copies of 2. So as a result, for the same number of neurons, you're actually going to end up with far fewer parameters than you would, because you get the division by 4 at the lowest layer, and that makes a huge difference, right? So I'm going to get far fewer parameters than in a non-distributed network with an identical number of neurons. Did that make sense to you guys? I'm assuming at least I lost at least some of you. So if I don't want to lose any of you, in the non-distributed case, I would have had something of this kind. So N2, and maybe let's say just I have 16 neurons over here, looking at my 8 inputs. The corresponding distributed version, which uses the same number of net neurons, is going to be, where is the eraser? It's going to be like so. It's going to be 4. Each of these is going to be 4. looking at 2. Why 4? This ensures that in the first layer, I have a total of 16 neurons, right? And so you're going to see that it's 4 times 2 times D, as opposed to 8 times 16 times 8 times D. And you can see how much the number of parameters went down, right? So 8 versus 16 times 8 is what? What is 16 times 8? 256, right? Or 128. So 128. So a huge difference, right? Now, so here is the comparison of the equivalent non-distributed net, and you will see that there's a huge change in the number of parameters.
Like the next layer, we'll have to look at more number of parameters.
No, so because this is 16, right? This is a total of 16. This is 16. So the next layer over here is going to have, how much would it have? If this is N2, it is going to be looking at N2 times 4 times 4, which is 6. It's the same. So the next layer doesn't change, right? So I can do the same thing again. So this would be your distributed scan in this case. Yeah, your turn. D is the dimensionality of the black little part. You can think of, you can think of this number of components in the spectrographic vectors, right? So you can see that. So this would be the shared parameter, the distributed scan. Yeah.
Small question. All these 4 blocks of 4 neurons, they all have shared parameters between them.
Yeah, they're all identical, right? Because you're scanning the input with us, something of width 2. So now, and you can see that if I distribute things over more layers, I'm going to get fewer and fewer parameters, right? Here's the other thing. Now look at the computation, right? At the first layer, so firstly, you see the distribution can greatly reduce the number of parameters in your net tremendously, right? Here's the second thing. In the first layer, you had those 4 blocks being computed. And in the first position, you had the 4 blocks being computed by the first layer, and the rest of them subsequently operated on those, right? When I shift the whole thing forward, I'm using the next 4 blocks, right? Do I have to recompute all 4 blocks? 3 of them are being reused, right? And so as I keep scanning forward, you can see what happens over here. Because I've distributed the pattern over 2 layers, I'm reusing computation. So not only is each neuron looking at something which is narrower, that's a saving in computation by itself. I'm actually reusing computation, which is an additional saving of computation, and that can be in orders of magnitude. So these guys reuse the blocks, 3 of the first layer blocks in the first location. I can do the same thing if I go over multiple layers, right? Here, if I decide to have the same number of neurons in my overall network, this is what distributing over 2 layers is going to look like. And again, you can, if you want to compare, look at the unique parameters. The highlighted ones are the unique parameters. And comparing the number of parameters with respect to the non-distributed version of it, it's going to be this one is 2D N1 plus 2N1 N2 plus 2N2 N3, which is very small compared to the much larger number on the non-distributed version. And also you can see how computation keeps getting reused all over the place as you go deeper into the network. So the benefits of distributed scanning are the benefits of distributed scanning are fewer parameters and a lot of reused computation, right? You find the same thing in the case of images. I have a lot of detail over here. You can go through the slides, but the point is you can actually end up having orders of magnitude fewer parameters. The exact arithmetic is irrelevant so long as you're convinced that that's what happens, right? And you can also end up with orders of magnitude lesser computation because you're going to be reusing. First, each of the units is looking at a smaller block. Each of the neurons is looking at a smaller block of the input. That is reduced computation by itself. And secondly, you're reusing the computation. So that's going to be a great deal of reduction in computation. So the key intuition is when you can get the distribution forces localized patterns, you can get orders of magnitude reduction in the number of parameters, and you can get huge gains from shared computation. But do not forget, regardless of the distribution, I can think of the entire network as scanning the picture with an MLP. All that happened was that I began having a distributed representation within the MLP itself. Now, this is important because this is going to show up in your quiz and your homeworks. Okay? So the scanning block, the new thing that we've learned is that the scanning block can be distributed over multiple layers of the network, which results in significant reduction of the total number of parameters. So I'm rushing through a few things, guys, because again, we lost 10 minutes too. Everybody? Yeah, okay. Great. What are the questions? So are there questions on Zoom, guys? Anyone with questions on Zoom? No, okay. Okay, what is it?
I was asking, so the non-distributed version does not get described.
Regardless of the stride. So the only difference between the non-distributed and the distributed version is whether the parameters are being shared within the subnet itself. So, but here, for example, in the pictures over here, both the non-distributed and the distributed ones are using a stride of 2. Yeah.
I'm confused how it's not losing information by reusing those parameters.
Clearly, every time you have fewer parameters, you're losing something, right? You're losing some capacity in the network. But typically what happens is that also results in a greater generalizability of the patterns it learns. So it ends up being to our benefit.
So is that like one of the hyperparameters you have to tune is like how much you reuse the parameters?
So that actually naturally falls out as an artifact of how you configure your convolutional neural network. So you will have some, when you work on your convolutional neural networks, you will often encounter something that's called a 1x1 kernel, a kernel that's 1 pixel wide. That's basically a non-distributed scan because it's only looking at 1 pixel and scanning with 1 pixel, right? Okay. So here is the answer. Distributed scanning enables hierarchical composition of patterns, which results in more generalizable models. It results in greatly reduced numbers of parameters and provides computational advantage through reuse of computation. Just some final touches. Again, I've rushed through a lot of things. I should be 10 minutes slower, but so we're going to look at some terminology and some other operations that are common. We will go over these in greater detail on Thursday. So the entire operation that we saw can be redrawn as maps of the entire image. You can say each neuron scans and redraws the input. So you can think of each neuron as looking at the input and thinking of it as a paintbrush, which picks up particles and drops the value on the output, right? So you can think of the first layer neuron just kind of scanning the input and producing their own mapped versions of the input. So they're basically repainting the input. The second layer neurons are looking at regions of the maps produced by the first layer neurons, and they're sort of scanning those together to compute their own maps. And the third layer neurons are doing the same. So each one of these you can think of as sort of redrawing the input, that it's looking at something and it's sort of redrawing it based on the presence or absence of patterns, right? So if you look at what is happening over here, the first layer neurons are going to be looking at boxes like the size of that little red box. The second layer neurons, which are looking at regions of the maps produced by the first layer neurons, are probably looking at inputs, at input regions the size of the green box. The third layer neuron is scanning the output of the second layer neuron, and it's going to be effectively looking at a region of the input shown by the yellow box. So each neuron is looking at some region of the input, and as you go through the neurons, the region of the input that they look at keeps getting larger and larger and larger. That is what is called each of the scanning neurons is generally called a filter. the filter scans for a pattern in the map it operates on. And the pattern in the input image that each neuron responds to is called its receptive field. So the first layer neurons, for example, might be looking at, say, looking for petals. So the receptive field is going to be something that small, and it's the shape of a petal. The second layer neurons may be looking at, putting together some petals to look at some partial flower-like shape. So it's that one's receptive field is going to be bigger, and the pattern itself is going to look more like a flower, right? And so on. As you go through the network, the receptive field of each of the neurons keeps getting larger and larger and larger. Now, what exactly is the pattern that they do respond to? It's going to be hard to determine, except for the first layer neurons. For the first layer neurons, the pattern of weights will tell you what pattern it's actually looking for. We'll see this in a later lecture. But then as you go through the network, to find out what the neuron is actually responding to becomes harder. So maybe we'll see some of that in the next class. Now, in the output, I've shown the outputs of all of the neurons. I've shown the outputs of from every single position on the input arranged as a flat vector, right? But what the output neurons actually produced was a map, the same shape as the input, if you follow the same pattern. So a typical final operation is to take this map and sort of rearrange them before you pass them through a final MLP. This is an operation that's called flattening. Again, you're going to encounter that in your homework. And another thing that can happen is we've sort of assumed, if we haven't actually focused on how big the stride is when you're scanning. So how much you move by is called a stride. And now, when you're speaking of a typical convolution, you're always moving by one position. So when I'm scanning for a flower, I'm going to be looking for a flower here, then take a single step, look for a flower, take a single step, look for a flower, and always move by just one position. But you can also take larger steps. And so very often you will actually encounter operations where you're taking larger steps, larger strides. Mathematically, once you begin taking larger strides, it becomes a lot more complicated to do your arithmetic. So we like to simplify things. We'll see that later. So CNNs with strides, it is sort of moving by strides. And here's the final bit. If I'm trying to look for flowers, and the higher layer neurons, they're trying to put together things like petals to decide if there's a flower pattern in it. Does it matter if the petal has jittered just a little bit? It shouldn't matter, right? So how can you account for some amount of jitter in the input? So let's say the first layer neurons are looking for things like petals. The second layer neurons is trying to combine a few of these petals together. But if you want to make sure that if the petal is off by just a little bit, you don't fail to fire. Now, one way to compensate for it is to have larger networks which account for all possible jitter. That's a very inefficient thing to be doing. So we again use the same principle that we are using at the output of the network to account for jitter invariance over here. We perform something called pooling, which says I'm going to look at a collection of these outputs. And these are all looking for maybe petal patterns, right? I need to detect if there's a petal somewhere over here. If any of these is large, then there's a petal here. So I'll just output only the largest value. So this is what they call max pooling. And so here, for example, if I had 4 outputs, 1, 1, 5, and 6, you just output a 6. And you'd scan the input using this operation to perform max pooling. And then you have the flattening and the classification there. This entire structure is called a convolutional network. We'll go over this in greater detail in the next class. The point of today's class was to convey the idea of why this entire model makes sense. Now, the traditional explanation given for convolutional neural networks comes from the perspective of biology. We're going to see that in the next class. But from a purely scanning for patterns perspective, which makes a lot of sense, this makes both mathematically, code-wise, structurally, and conceptually, it makes a lot more sense to think about it from that perspective. So I'll stop right here. We'll continue in the next class. Thank you.
Yeah.
280 slides. Was I speaking too fast?
Oh, no. Go back, go read the slide, and all my questions on the lecture.
It wasn't confusing, was it? Okay. Stop the recording.